polynomials. And Taylor polynomials are what? An approximation for a function. Yes? So if they're an approximation, are they an exact equivalent to that polynomial? No. Which means that there is going to be some sort of error in it, right? Just like with our alternating series, there was an error when we started looking at approximations. Here, there's also going to be an error because a Taylor polynomial is an approximation. You don't have to necessarily write this first part down. But basically, if I have an f of x, okay, and I'm using my Taylor polynomial of nth degree to approximate that, there's going to be some remainder that would be left over, okay, to get me the actual function. And just as a reminder, remainder and error are used pretty interchangeably, meaning that this remainder here is also what we call our error. So you'll see both of those as far as give the error of the Taylor polynomial or give the remainder of the Taylor polynomial. And if we look at this, basically it's just going backwards. My remainder is going to be f of x minus my p sub n of x. But we're not really going to use this a whole lot because that means that I have to have my f value. I have to have the exact value in order to find my remainder this way. Agreed? Which the whole point of using a Taylor approximation is that I don't want to have to find the exact value, so finding the remainder that way is not super helpful. Which is why Lagrange then came up with a theorem that tells us an inequality that we can use, kind of like we did for our alternating series, of I at least know that my error has to be less than this. So we can at least know how close our approximation is. Are we all with me there? Okay. So looking at that, there's a lot going on here. So digest, then write. So it says if a function f is differentiable through order n plus 1 in an interval I containing c, then for each x in I there exists a z between x and c such that the following is true. That's a lot. Okay. So what's going on here? Notice that this f of x, okay, so notice that this first part here would be my Taylor polynomial expansion. And then this ending part at the end is my remainder. Are we all with me then? Yeah? Okay. So notice this is very similar idea that we looked at when we looked at our alternating series error, is that if I'm looking at the nth degree polynomial, okay, what comes next is going to give me my remainder. So notice that my n plus 1 here, right, is the next term. Okay. And this is basically our Taylor polynomial expansion for the next term. So f to the n plus 1 is the n plus 1 derivative. N plus 1 factorial is just because I have factorials on the bottom, and then my x plus c to the n plus 1 power, again, is just from my Taylor polynomial. Now, this z is a little bit funky. So basically what's happening is, okay, I am finding some remainder, right? And my goal is to evaluate that at some x value. Yes, like that's the purpose of this, is to help me find approximations of x values. Yes? No, maybe. Okay. So I know that my z, so remember this c is what we are centered at, okay? So we are looking at the interval from whatever x value I want to plug in there to wherever I'm centered at, or vice versa, if our c happens to be smaller than whatever x value we're plugging in there. And so basically what it's telling us is that there has to be a z that lives somewhere in here that I can plug in there to find my remainder. Okay, we don't usually actually have to find the z, so we don't have to worry about it a ton. For the most part, what you need to remember is that we're looking at the next term there. Are we all okay with that? But like I said, this would be the exact remainder, which is not usually what we're finding. What we're finding is this inequality instead. So notice that this is very similar to what I have here. Okay? The only thing that we've added is that I'm looking at the maximum instead. And the reason that we're looking for the maximum, okay, is because remember that Taylor polynomials, right, are polynomials. So for our alternating series, they were just values. And so I knew that I had to be smaller than the next value. Here I'm looking at a full-on polynomial. And so, right, the next term might be here, okay, but it has a maximum up here. So I have to use the overall maximum value instead of just being able to plug in the next value. And it makes a little bit more sense once we actually start looking into it. So, for the most part, this is what I would write here. That's what we're going to be using most of the time. So if you want to put a star next to that, if you wrote both of them down, that's fine. But you mostly just need to know that inequality. And no, there is not a nicer way to write that. So that's how you have to write it out. Do we have that down? No? Waiting a second? All right. Because like I said, it makes a little bit more sense when we actually have numbers to plug in there instead of just variables of everything. So, we have the function f has a continuous derivative for all real numbers x. Assume that f of 3 is 5, f prime of 3 is 2, f double prime of 3 is -4, and f triple prime of 3 is 7. So our first part just says to write a third degree Taylor polynomial for f about x equals 3 and use it to approximate f of 3.2. Give 3 decimal places. This is calculator x. So what is the about x equals 3 mean? That's our center. That's what we're centered at. So this is a Taylor polynomial and not a Maclaurin because we are centered at 3 this time instead. Which is why they give us our f primes and f of 3. So I'm looking for p sub 3. Equals, what's going to come first? F of 3, which is 5. Then I'm going to add. That's going to be my first derivative, which is 2. And we would divide by 1 factorial, right? Which is just 1. So I just end up with a 2 there times x minus c, which again our c value is 3. Okay. Plus, what's our second derivative at 3? Okay, and I'm going to divide by 2 factorial, which is also just 2. Okay. And again, this time I have x minus 3 to the second power. And then our last term, I have plus my third derivative at 3, so 7 divided by 3 factorial, which is going to be 6 times x minus 3 to the third power. So that part right there is very easily non-calculator active, right? Like I could have been given those function values. You could have left that as 2 factorial and 3 factorial, and we would have been fine with that Taylor approximation. The reason why it's calculator active is that next part, okay, that we are looking at plugging in a 3.2. Are we all okay if I tell you what that value would be if we just plug it in? Yes? Okay. I'm just plugging it in for all of my x's. And you type that into your calculator. And so we get that at p sub 3 of 3.2 is 5.329. Okay. So that first part's very similar to what we've been doing. The only part that's a little bit different now is that we plugged in the 3.2. So on this next part, it tells us that the fourth derivative of f satisfies the inequality that the fourth derivative of a is less than or equal to 35 for all x in the interval 3 to 3.2. Use this information to find a bound for the error found in part A. So there's a lot that's going on there. And so we kind of have to break it down. I would start by just writing out our formula. Okay, that's a good place to start. So we're looking for our error, which we said is also our what? Remainder. So I'm looking for my remainder sub 3 is less than or equal to the absolute value of the maximum of f to the, or the derivative of n plus 1. If I'm using the third remainder, then what's my n plus 1? 4. Divided by, and then on the bottom we have n plus 1 factorial. But we said our n plus 1 is what? 4. So I get a 4 factorial there. Times x minus c. So what are we centered at? 3. And it's to the, again, n plus 1, so fourth power. End my absolute value. So at the end of the day, our goal is to plug in this 3.2 to find my remainder, okay, into this x right here. Are we all okay with that? So that's why there's still an x there, because then I can figure out what the remainder had to be less than for any x value that we were approximating, which in this case is 3.2. The problem right now is that we don't have a top value. My 4 factorial is fine. I have a 4th, that's fine. But I need some value to plug in on the top there. Bless you. Are we all with me there? Okay. So this time it tells us that our 4th derivative has to be less than or equal to what? 35. So that means that 35 is going to be the what of my 4th derivative? The max. And so that's what we're going to put there. Are we all okay with that? Yes, nobody? So again, that's my general remainder sub 3. But they asked us then to find the specific error bound for our error that we found, or sorry, for the x value that we used in part A, which was 3.2. So then, same kind of as before, I'm looking at r sub 3 of 3.2 is going to have to be less than or equal to, I'm just going to plug in my 3.2. So I have absolute value of 35 divided by 4 factorial. This is kind of like with most of our approximations, right? It's going to be a number that's pretty close to 3. So it's usually a pretty easy decimal to figure out. What is 3.2 minus 3? Just 0.2? Yeah. Okay. To the 4th power. Now that's going to end up being positive, so we'll be able to drop our absolute values. And again, we're just plugging all of that into our calculator. Again, because this is calculator active. If it was not calculator active, then again, we could just leave this here, right? Like none of that was super hard in and of itself, right? Just plugging in values, and you would just leave your answer as that, okay? But since it is calculator active, I can actually get a value there, which is going to be 0.00233. So we know that our remainder, or our error, has to be less than or equal to that. Or in other words, that up to 2 of our first 2 decimals have to be correct. Because I have 2 zeros in my decimal approximation. Are we all okay with that part? What questions do we have until that part? There's just a lot of plugging and chugging with these. Like, the formula looks funky, but once you kind of figure out what each one of those pieces means, then you're just plugging in. So then for part C, it says find an interval between A and B such that f of 3.2 has to be between those 2 values. So again, we said that this is the remainder or the error. Yes? Are you with me? Okay. So if this is what I got my actual approximation as, yes? And I know that the absolute value of this has to be less than or equal to 0.00233. What would I do to find that interval? Plus or minus what to what? Correct. So I know that on this side it would have to be 5.329 plus our remainder. And it's going to have to be greater than 5.3229 minus our remainder. Are we all okay with that idea? And that's why we have the absolute value around our remainder, because then it can give us an interval, because I do have to have something on both sides. It's not just going to be an upper bound. So if we were to plug that in, we get that our interval is going to be between 5.327 and 5.332. What questions we have there? Alright, what do we think about part B? Can f of 3.2 equal 5.331? Why? Yeah. It lives in that interval. So we're good. What about the second part? Can f of 3.2 equal 5.334? Why not? Yeah, and so that would mean like we would have a different error, yes? And since this is a theorem, that tells us that our error must always be less than that, which means that that would break my theorem, which it's not a theorem if it's wrong. So we know that that could not be that. Yes, no, maybes. So really the biggest part of this, or like what's going to change from problem to problem, is how we find this max value. And it can be given to you a couple of different ways. This one was just given to us, right, that it is 35. We can also be given some sort of function where we should know what the maximum value is going to be. Or lastly, we can be given a graph. So we're going to look at a function first. So it says the third Maclaurin polynomial for sine of x is given by p sub 3 of x is equal to x minus x cubed divided by 3 factorial, which remember we found earlier in this chapter, or in this section. It says use Taylor's theorem to approximate sine of 0.1 by the third polynomial of 0.1 and determine the accuracy of that approximation. Alright, so what's that first part asking us to do? Plug in 0.1 for what? X. Yes? And so we get that this is approximately 0.09983. Finding the approximation is usually not the hard part. Again, it's that second accuracy approximation. So I have r sub 3 of x has to be less than or equal to what goes on the inside here. What goes on top? Okay, maximum of f, and then what's my next, or what's my n plus 1? 4 again. Of z divided by, what's on bottom? 4 factorial times, it's just going to be x to the 4th. Are we all okay with that? Because we have a Maclaurin here, so my c is 0. Yes, no, maybe? And our goal is to plug in what? Okay. But what do I also have to be able to plug something in? Something for my max. But the other two are pretty straightforward. And this is one of the times where we should know what our maximum is. Why does it have to be 1? That's as big as sine gets, yes? So remember that this approximation is for sine, yes? So it really doesn't matter how far out I go, but specifically in the interval between 0 and my x, which would be 0.1, it's not going to get bigger than 1, so I can put my 1. And that actually equals 1 divided by 2, 4, 1, 2, 3, 4 zeros, which is also 6. So how accurate is that approximation? Pretty accurate. Which, if you think about point 1, is pretty close to where we're centered at, towards 0. And remember that when we were looking at our graph, right, when we started building out that Taylor polynomial, yes, as long as we're kind of centered around 0, that Taylor polynomial was fairly accurate to my sine graph as long as if it was relatively close to 0. The farther out we go, the more terms we would need, which is why we have something that's pretty close to 0.
Will most sine and cosines be Maclaurin's? Is it just?
They're a popular choice for Maclaurin's. I would say if you're not centered at 0, then you're going to be centered at something that's like a pi over 2 or something like that. That would also be relatively easy to figure out, if that makes sense. So they're usually not going to give you something just like off the wall. What questions do we have on this one? Alright, that's where we're going to stop for today.